Alright then, so let's start by modelling the drag force. So this is also referred to as the axial force, or the force in the XS direction. So that's the stability axis system in the X direction. So you'll just recall the, oh sorry for the squeaky chair. You'll recall this figure that I just showed on the slides, and our drag force here, which is opposite in direction to the X stability axis, and we call that drag force D subscript 1 for the drag associated with the trim condition, and we give it the name F subscript A for aerodynamic in the XS axis, and it has a subscript 1 also associated with it for the trim condition. So that's what I've started with over here. And recall, of course, that we can describe drag as the drag coefficient multiplied by the dynamic pressure multiplied by the wing reference area. So again here, subscript 1 on the drag coefficient is the drag coefficient associated with trim condition. So at a particular flight condition, namely a Mach number and Reynolds number, the drag coefficient in the trim condition is a function of angle of attack, the elevator deflection angle, which we call delta subscript E, capital E for elevator, and the inclination angle of the horizontal tail. Or if we have a fully moving horizontal tail, stabilator, this refers to that angle as well. So as we change any of those three parameters, we're going to change the drag coefficient, right? So we could also include the inclination angle of the wing, I subscript W, in this little formula here. But as you will see in a moment, if the inclination angle of the wing is constant, then it just gets eliminated from our equation because it's constant with respect to angle of attack, which generally is the case, right? Unless you've got a very strange aircraft which has a whole wing that's able to change its inclination angle with respect to the fuselage, right? So what we do is we apply a Taylor series expansion to the expression for the drag coefficient. So we expand this out and linearize about a small perturbation in the trim angle of attack. So we get this expression here. So CD0 is going to be the drag coefficient associated with the trim angle of attack. Then we have these three extra derivatives here, one with respect to angle of attack, one with respect to the with respect to the elevator deflection angle, and one with respect to the inclination angle of the horizontal tail. And then if we assume that this is our reference condition, so our reference condition is going to be alpha 0, delta subscript E0, and I subscript H0. So what I mean by a reference condition is these terms may not actually be at 0 degrees with respect to the body axis system, but when we choose our trim condition, we set each of these equal to 0, and then we measure them, the changes in all of these angles with respect to that reference condition. Okay, so where we go from there is, well, first of all, I've labeled what each of those derivatives are. So instead of writing the partial derivative of drag coefficient with respect to alpha, I've changed the notation to just be CD subscript alpha. So I get something that looks like this equation, right? And I do the same for the deflection angle of the elevator and for the inclination angle of the horizontal tail. And those those derivatives are all referred to as drag stability derivatives, but with respect to a different variable. So with respect to angle of attack, with respect to elevation deflection angle, and with respect to the angle of the horizontal tail. So one small assumption to make here is that the effect of these two is much smaller than the effect of that one. So of course, if we change the elevator deflection angle, we're going to change the drag on the aircraft, and the same if we change the inclination angle of the tail, right? But the effect of doing that is much smaller than the effect on drag if we change the angle of attack. So because we assume that these two are small compared to this one, we assume that these are negligible and remove them from the equation. So we're just left with these two terms on the right hand side. So that's the equation that we get from just applying a Taylor series expansion to our initial equation over here, which we started with, which just came straight from the definition of drag in the stability axis. Well, there's another way that we can formulate an expression for the drag coefficient, and that's using something called the Prandtl relationship. So the Prandtl relationship says that the drag coefficient, in this case in the trim condition, subscript 1, is equal to the parasitic drag. So recall that is like the form drag, which is the drag associated with the physical shape of the body, and that also includes skin friction as well. So the parasitic drag plus the induced drag. So that's the lift-induced drag due to the redirection of airflow in order for the aircraft to produce lift. And you can see that the induced drag here, because we have aspect ratio on the bottom of this fraction here, the induced drag is lower for higher aspect ratio wings, and also the induced drag is lower for wings with an elliptical lift distribution, because that's associated with this parameter here, E, which is called the Oswald efficiency factor. And that is a value between 0 and 1, depending on how close the lift profile of the wing is with respect to a perfect elliptical lift distribution, right? So for a perfectly elliptical lift distribution, the Oswald efficiency factor is 1, and then it reduces as the lift distribution deviates from an elliptical shape, right? So where do we go from there? Well, we essentially want to equate our two different expressions for CD1, right? So we had one expression that came from essentially the definition of our stability axis, so namely this one, and now we're going to have another expression for CD1, and eventually we're going to try to equate these two things. So the only problem that we have with this at the moment is that this CD0 bar is a different CD0 to this one, right? And that's what I'm going to explain right now. So CD0 bar is different to CD0 because CD0 is the drag coefficient associated with this particular condition here. So when the angle of attack, the elevator deflection angle, and the inclination angle of the horizontal tail are all 0, whereas the CD0 bar term is CD0 when the lift coefficient is 0. So essentially we have two different approximations for CD here. We have a linear one and we have a quadratic one, right? So if we plot the drag versus angle of attack, we have this linear one here where the y-intercept on the CD axis is going to give us our CD0, and then we have this quadratic one because CL squared depends on alpha, right? So we have this quadratic function here, where its intercept with the y-axis is going to be this CD0 bar. So one assumption that we can make is that for small alpha, these two things are close enough that we can just take the linear approximation, and that's going to become acceptable for our particular region of angle of attacks that we're going to consider. Obviously, as we increase angle of attack further, these two lines are going to get further and further apart. But essentially, these 2 points here are going to be equal to each other if the aircraft has symmetric aerofoils, because if an airfoil has no camber, the lift coefficient is 0 when the angle of attack is 0. So we're going to use those couple of assumptions to just go ahead and equate our two expressions for the drag coefficient CD1, and just cancel out these two terms based on those two assumptions. And we get left with this thing.